Welcome back, class. Let's begin with covering a few things that we need to touch base with before we move into the next material. A few last tidbits. One last thing on behavior. I want to distinguish between molar versus molecular views when it comes to ideas of behavior. Skinner's views of behavior is most often characterized as a molecular view of behavior. That is, behavior can be decomposed into atomistic parts or molecules. Atomistic parts or molecules. Skinner proposed that a complete account of behavior requires our understanding of selection history at three levels: biology, natural selection of the animal; behavior, the reinforcement history of the animal; and for some species, culture, the cultural practices of the social group to which the animal belongs. So that's the molecular view. The molar behaviorists, they argue that behavior cannot be understood by focusing on the events in the moment. That is, they argue that behavior is best understood as an ultimate product of an organism's history, and that molecular behaviorists are committing a fallacy by inventing fictitious proximal causes for behavior. So molar behaviorists argue that the standard molecular constructs, such as associative strength, are better replaced by molar variables such as rate of reinforcement. Thus, a molar behaviorist would describe loving someone as a pattern of loving behavior over time. There is no isolated proximal cause of loving behavior, only a history of behaviors. So, wrapping up some of the ideas from our last session, we discussed Russian impact on behaviorism with Sekhanov as well as Pavlov. We also discussed some of the hardcore beliefs held by John Watson, the idea that he really was a major proponent that psychology should only focus on the objective, the observable, and he really held this as a really strong belief as he wrote his Behaviorist Manifesto. Then we touched base with McDougall. And McDougall, a behaviorist, but he was a behaviorist that said yes to some mental aspects, so he did not want to ignore them, that they do have some sort of value. We then discussed briefly Guthrie in his One Trial Learning, followed by Hall. And Hall produced this idea of intervening variables. And this intervening variable that Hall proposed, however, was a physiological one. He proposed that between a need and behavior, there was this intervening variable he would refer to as a drive. Then we looked at B.F. Skinner and all the good works that he did. Tolman was then introduced when he looked at the role of purposive behavior. You have intent to do something, and he looked at other intervening variables which sort of opened the door again to this idea of cognition or cognitive aspects. Behaviorists had a difficulty dealing with cognitive aspects of human psychology like thought and language. So the idea is they attempted, as did Watson, to try to describe all sorts of things, thought and language, in terms of behavior or mental talk going on in one's mind. This was something that was rejected by some. Now, the idea is that behaviors was not the answer to everything. In fact, the behaviors like Watson probably tried to carry it too far. But the state of behaviorism today, Skinner was considered to be the most influential behaviorist, as well as some would say one of the most instrumental and influential individuals in psychology, period, in the modern era. Current challenges still do exist within the area of behaviorism, but they still remain a strong force in psychology. Today, in this session, we'll be linking behaviorists to Tolman and then to cognitive psychology. But first, let's look at some cognitive ideas, to preview some key cognitive ideas to sort of set the stage. The start of the revolution, cognitive maps, insight, animal minds. Questions of concern were, do animal and non-humans and humans think alike? So do animal non-humans and humans think alike? Question. Can we learn about us from examining them being animals? We saw some earlier research and findings from Tolman and his latent learning, Kohler and insight learning when it comes to chimpanzees, and lastly the idea of transposition, where we have this notion of transfer training from one thing that we learn, and we can, whatever we learn from one thing we can apply to another item, another solution, another situation. So Darwin's view of mentality, he saw the difference between humans and animals is one of quantity, not quality. So we have just more mentality, more capability, even though it's the same type of thing that animals may have compared to humans. The debate was about anthropomorphic explanations, where it is that we see an animal behave in such a way and then we attribute to that animal human-like characteristics or intentions. They wanted to try to move away, to eliminate such explanations to be more scientific. We saw that with Ernst Mach. We should avoid such language with non-humans. Or Romans, where he cautioned that removing all anthropomorphic terms removes the explanation itself. So he was sort of cautioning us against the idea that by removing everything, then we lose the main message and the main idea that we're trying to explore. So Tolman. Now, a couple of things about Tolman. The idea of rats in a wheelbarrow. So if you would, imagine a bunch of rats placed in a wheelbarrow. And then somebody's using that wheelbarrow that contains the rat, and they run through the maze. So they ran through a maze equivalent times it took rats to learn the maze. So some rats actually ran through the maze and learned it that way. And then there was a group of rats that were put into a wheelbarrow and they were carried or driven or rode through the maze. So these wheelbarrow riding rats, when finally allowed to attempt the maze, they quickly solved it. Now the point here is this. There was no motor activity required to learn the maze for these rats. This was a contradiction to the mechanistic behaviorist approach. They would say that you physically running through that maze, part of the mechanism of learning it was the actual running through the maze, and so you were able to duplicate that later to demonstrate that you learned that particular maze pattern. But in this case, no. There was no motor activity at all. They sat passively in the wheelbarrow as something else took them through the maze. So the same rats who learned to run the maze could also swim a maze. So they took that from running the maze to swimming the maze. So it's a totally different modality altogether. So now they're swimming, not running. So we have rats that were carried through the maze, some that ran through the maze, and some that swam through the maze. They were all able to do it. So if the maze was covered, the rat would straight line to the goal. And remember, the goal of a maze is that there's usually food, some sort of treat at the end of the maze. So in this instance, you have this rat, and they cover the maze. Okay, so imagine, if you would, they put a big platform or something on top of the maze. The rat is placed there. As opposed to running the maze in their mind, they just go straight to the treat. So if the maze was covered, the rat would straight line to the goal, not mechanistically walk the maze as it was learned. So here, what Tolman was demonstrating is the key of all of this was the goal, the food at the end. Okay, so learning is the formation of the proper representation. The notion is that we saw that there is something else that demonstrates that we are learning. It's not just some sort of behavioristic, mechanical type of thing for us to learn. So, a couple of other ideas I want to preview is IA, artificial intelligence, and the neurocognitive revolution. Quick background. So now we have this understanding that Tolman produced that there's something else going on. It's not just all behavior, and we'll get back to that later. But now we're looking at, okay, what is a brain? What is artificial intelligence? Okay, and again, the idea would be is that when we talk about artificial intelligence, we're trying to replicate a human brain or a human mind. So, if processes of the brain leads to mental life or to consciousness, So the brain's physical processes lead to this thing we call consciousness. Then if we can duplicate it in a machine, why shouldn't it work? Why shouldn't they be intelligent? So if we're able to duplicate the physical characteristics that exist within us, but we can create that within this silicone chip or this processor, why should they not also be intelligent, this machine mind? So we have expert systems that can match and beat some human capabilities. Okay, in this one specific area, they can do that. On the surface, the cognition of machines, the thinking of machines, can be indistinguishable from human cognition. If so, human features can be reduced to component parts. We are reducible. The idea with reducibility is the notion that we have this thing, like say consciousness, and we can reduce it to its parts. So, we then talk about information processing theory that was offered by Shannon and Weaver, and also Alan Turing, which we'll see a little bit later. Turing's first of all, information processing theory is how we start to see how it is the human mind works and processes things. Turing's philosophical approach, he was a brilliant man from decades ago around the era of World War II. He asked the question, how can we determine if a machine is intelligent? What if we could not distinguish from the communication of a machine from that of a person? You know how it is these days. You could be answering your phone and someone's talking to you and you're answering their questions, and you ask them questions and they respond to it, and then shortly you'll realize, hey, I'm talking to a machine, a computer program. Alright, so he understood what we are now probably demonstrating today in real life when we answer the phone and it could be some sort of robocall there. So what he was asking, what if we could not distinguish the communication from a machine from a person? The key point that he was offering here is this: conversation is a complex process with many pitfalls. Sometimes you may misunderstand something. Maybe there's slang that's involved, a slang that you're not familiar with. So there's many ways in which communication and conversation can falter. So in order to maintain a conversation, you have to have some degree of capability. And what they're talking about here is some degree of intelligence. So to be able to navigate conversation is a sign of intelligence. An intelligence that takes time to develop, as we saw with Jean Piaget and his views of how it is that we develop cognitively from birth to adulthood, so to speak. So it is proposed that a specific mental property can be achieved by different physical properties. So we, in our human brain, we have neurons, whereas a computer brain, a computer intelligence, they may have circuits. This is referred to as the principle of multiple realizability. So if the thing that makes us conscious is a very complicated pattern of neurons and connections, if we're able to duplicate that with computer circuitry, okay, then are we able to produce the same property of consciousness that we see in us? That's the basic premise there. So, if this is indeed the case, if we are ever able to do that, then that brings up another concern that we see often portrayed on television shows and movies and sci-fi novels and things of that nature. An ethical concern of artificial intelligence and rights. Eventually, we must ask, if we are able to create thinking and intelligent machines, what do we do? Do they have rights? Do they have responsibilities? So that is if we're ever able to create an artificial intelligence, something that truly thinks and has all the states of mentality that we humans possess. So there are arguments against this, however, some strong arguments. So the arguments against AI or artificial intelligence. One is this: human intelligence is more than computations. You can't use a system to explain everything about that system. And there's this idea of something called incompleteness theorems. An axiom is like a computer program, okay? You can have a bunch of axioms, and these axioms can be part of a computer program. And the idea, if axioms don't contradict each other and are listable, some statements are true but cannot be proved. That's one of the incompleteness theorems. A system of axioms cannot show its consistency. Think about it, it's somewhat of a heady idea, but what it comes down to is that you can have all the programming in the world, all the computer script in the world, but the script is going to always be incomplete. Some statements are true but can never be proved. Just think about what that means if you're programming something, that it can't be consistent. It can't show its own consistency. And the idea is that this is a fundamental issue that some see as a problem when it comes to belief that we could literally program an artificial intelligence. Then we have this, Cyril's question. Cyril, what exactly is an AI device doing when solving a problem? What is an artificial intelligence doing when solving a problem? He offers a thought experiment. This thought experiment is what he refers to as the Chinese room. There is a video on that on your Canvas site, so be sure to review that. Alright, so the Chinese room involves sorting and compiling based on specific instructions. So the idea here, the premise is you have somebody locked in a room, okay, and you can slide information under the door and ask them questions on a piece of paper, and the person in the room has all these algorithms and instructions about if you get this, you can do this, that, and other thing, a list of things to do in order to respond as if they can answer that question. So they have scripted programming inside that room that helps them address the questions that are being asked on outside the room and being slid under the door. So it involves sorting and compiling based on specific instructions. There's no need for understanding or meaning in this scenario. The person doesn't have to understand anything. All they have to do is to understand the instructions, what to do. They don't know what they're saying and responding to the Chinese characters that are being slid under the door. They see these characters and they use whatever algorithm and instructions they have inside that room in order to respond to it. There's no need to understanding the meaning. There is no intention by the person in the room. There is no possibility for gaining meaning from such an individual in that room. And what he's proposing here is that this is what's going on in an AI system. They're simply following instructions, but the instructions does not mean that they have any type of understanding. Therefore, because that's the way computer systems work, there's no way that we can truly have an artificial intelligence. So all meaning is, further ideas that go against it, all meaning is social and contextual, meaning that if we think about things that we know from conversations and how we speak today and how you'll speak 10 years from now and how you speak 10 years previously, if you're old enough, you could remember that. All meaning is social and contextual. What you say may change. How you say things may differ. Meanings arise out of cultural interactions. Okay? Some of you may not understand some of the things I'm about ready to say. That's whack, or some of the other expressions. That's cool, or something, or that's fly. All these things you may remember, but they may not have any meaning or the same meaning that they did previously today. Alright? So meanings are socially constructed. So for instance, we have these terms for those of you who do a lot of texting, okay, and IMing, ROFL, rolling on the floor laughing, STFU, LMK, ILY, YOLO, SMH, LMFAO. All these You learned, and it's part of the process of learning, and it allows you to converse, okay, demonstrating intelligence. So here, language is a social phenomenon. Meaning is extracted from the social interactions of a particular culture. Such as an AI system will require engagement in the shared practices of the culture to really, truly be an AI. And that would be something that may be somewhat difficult. Now, that gives us some of the arguments against this stuff about thinking and how AIs may work or how AIs may not work. But I want to also touch base on something that you've covered in previous classes most certainly. The ideas of cognitive development, how it is that we humans cognitively develop, and this is sort of a flashback. So, two individuals who are normally going to be discussed when we talk about cognitive development. We have Vygotsky, which you don't hear of that much, and we have our friend Piaget, which you hear quite a bit. And just looking at these real quickly here, comparing the two, the social cultural context, Piaget does not emphasize that much, but Vygotsky does. Constructivism, a cognitive constructivist, basically saying that the cognition is the thing that builds to make your cognitive development, whereas Vygotsky sees it as very social. Stages, strong emphasis on stage development, no general stages proposed by Vygotsky. The idea here is that we see the role of language for Piaget is very minimal, but very major in Vygotsky. So I just want to make sure that you recall some of the things about how it is that we do develop our cognition, as we've talked about this artificial intelligence. Okay, so let's get on with it. We're going to be talking about cognitive psychology. We'll do a few tidbits. We'll talk about intervening variables, some early influences, including Chomsky's language acquisition device, the cognitive revolution. We'll revisit again some more information on artificial intelligence and Turing and the Turing test and Cartesian challenge, and move on and introduce the idea of cognitive science. So, tidbits. Chomsky. Restricting psychology to the observable is unnecessary. So remember our previous chapter, we were all about the behaviorist, okay, the hardcore behaviorist, and so now we're seeing people starting to pull away from the major behaviorist influences of the day in the Americas. So we see now the cognitive being built back up. Tolman's ideas of intervening variables, this notion of neo-behaviorism, proposive behaviorism, a branch of psychology that was introduced by Tolman. It combines objective study of behavior while also considering the purpose or the goal of behavior, which is really sort of like motivation in a sense. A very cognitive idea and something that we don't see objectively. All right? So we see in here these stages of setting up the idea of psychology going back to cognitive areas and cognitive exploration. So real quickly, we'll wrap up this idea of Tolman's intervening variables, and then we'll go to the next session. So Tolman's intervening variables. Intervening variables are hypothetical internal states that are used to explain the relationships between observed variables, such as the independent and dependent variable. So remember, the independent variable is that thing that we manipulate in some fashion with the belief that it will have some influence on the dependent variable. So we know what we put in or what we change in the system, and we know what we're reading or measuring in the system, being the dependent variable. Change IV, read or measure the DV. So what happens in between? And that's what Tolman was talking about. He was talking about intervening variables. The thing that happens in between the independent and the dependent variable, the thing that is key, of great importance, is going to be either learning, memory, motivation, attitude or personality, or traits of some sort. So the idea here is that he's saying it is important to know what that intervening variable is. So now cognitive aspects are part of the work of psychology. So, experiment by Tolman and Hanzik, 1930, on latent learning in rats. Specifically, the group that received a reward every time they reached the goal box. One of the independent variables was the number of practice trials the rats received. They got one trial per day, so each rat got an increasing number of trials. The dependent variable was the number of wrong turns or errors the rats made on a trial. And the following graph shows a relationship between the independent variable and so practice trials, independent variable. Errors should go down, and as we see, the errors do indeed go down. Theoretically, an internal state of, quote, learning intervened between the independent variable and the dependent variable. The rats learned something. Learning the intervening variable. It was this state that caused errors to decrease, not practice trials. So from a behaviorist point of view, it was practice trials. We increased those and then fewer errors. Here they're saying it was the state that caused errors to decrease, not the practice trials, not the behavior of going through the trials, but something we call learning.